I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on motion maps. Video, we're going to talk about motion maps. Motion map is a diagram that represents objects in one dimension, meaning that it's just moving in a straight line. The motion is represented with a series of dot placements, and the dots are starting points for vectors, an arrow that has a defined length or magnitude and direction. Vectors and dots are placed above the dots to represent other parts of motion. We'll go through some examples to talk about that. So the symbols are the schema on a motion map. The dots represent two or more parts of motion, but the main two parts of motion that they represent is the positioning of the moving object. It's where the dot is placed above the position axis for the motion map. And so the dots also represent an increment of time that passes. So the time that represents the number of dots, the first dot always represents time equals 0 seconds. So that means for each succeeding dot, it represents some increment of time. The time increment between dots can be any time increment. The standard time is 1 second, but can be defined differently to simplify the drawing. So for example, if an object's moving for 20 seconds, we can simplify that and say each dot represents 4 seconds, so we don't have to draw a whole bunch of dots. Also note that since we're starting with 0 as the first dot, you're going to need one more dot the number of seconds if you're using 1 second. So 4 seconds would represent by 5 dots. And the dots can also represent a 0 velocity or 0 acceleration. We're going to go through those in the examples. So there are also going to be two sets of vectors that we're going to draw on a motion map. The first set of vectors is going to represent the velocity, and those are going to be the velocity vectors. The velocity vectors are also going to have defined length and direction, and it starts on the dot and points away, showing the object's direction of motion. And the vector should extend all the way to the next dot. And then the direction the vector points shows the direction of the object's motion. And then the length of the vector, or the magnitude of the velocity vector, represents the speed. So if it's getting longer, it's getting faster. If each vector is the same length, then it means it's moving at constant speed. And if they're getting shorter, that means it's slowing down. So the longer the vector shows a faster speed. We also have acceleration vectors, and one acceleration vector is going to be drawn above each dot, not starting on the dot, but drawn above. And it's going to be drawn a little bit differently to distinguish between the velocity vectors and acceleration. It's just going to be drawn with one line to represent the arrowhead. And the length of the vector represents the value of the acceleration or the magnitude. So what we're going to do to draw those acceleration vectors is we're just going to, like I said, just draw one line on the arrowhead like this. So how are velocity and acceleration drawn on a motion map if they're 0? So we said that the length of those vectors represent the value of the velocity or the acceleration. So how could we draw a vector of length 0? So thinking back to geometry, what's something in geometry that doesn't have a length? Well, the only thing that doesn't have a length in geometry is a dot or a point. So we're going to represent 0 acceleration and 0 velocity with a dot, just like we do for position and time. So let's go through a number of examples. So the first one, we're going to start with just an object moving in a positive direction at a constant speed. So you can see as the car starts moving, we start placing dots in front of the car. And you can see that the car moves the same increment each time. So you can see, we'll blow that up and you can see the dots are about the same increment apart. So we're going to use that to draw our motion map. So here's our motion map axis. That axis represents position, not to be confused with anything else, but that axis represents position. So where we place the dot shows where the object is. So we'll define a 0 point on there. And it doesn't matter the increments that what each represents. It's just a qualitative representation. So you can see the dots that are placed along the ramp. We're going to go ahead and place the dots in the same spot, starting at a position of 0. So the first dot at position 0, and each succeeding dot lines up with the dot above it on the ramp. The dots were placed in front of the car as it was moving across the ramp. And now we're going to add those velocity vectors in. So we're going to draw those arrows to extend all the way to the next dot so that there's no confusion about the length of the vectors. So if we always draw it all the way to the next dot, we know how long the vectors are. And if there's equal space between the dots, that means equal length velocity vectors, as we have in this case, showing constant speed. Now remember that first dot is time 0. So when we start counting time 0, then time 1, all the way through, you can see that we have 6 seconds of motion represented here, but there are 7 dots. So you need one more dot than time is shown in terms of motion. And you can see that the spacing between each of those dots is the same. They're reaching each third line away from 0, showing that it's moving the same distance in that same time. So here's another example. We're going to draw a motion map again for a car. This time it's moving only for 5 seconds at a constant speed. Then it stops for 3 seconds. And then it turns around and moves back in its same direction for 4 seconds. So you can see the dots being placed. There, the objects being stopped and set back down in the starting position. And we'll enhance that and blow that up. You can see that the position and time dots, how they're placed in on the ramp, you can see that it's lined up. So we're going to start our position at 0. It doesn't always have to start at 0, but we're going to start it at 0, and we're going to place those dots to line up. And then you can see it reaches this spot. That was the point where the car was picked up. So at that point, it stays in that position for a period of 3 seconds, as we showed. So we're going to go ahead and, just as we kept drawing dots there, it did not move at all. So we're going to place those dots and stack those dots just as you see on the picture that was created. So you can see that to represent 3 seconds, we have 4 stacked dots. Remember that first dot, if we were start the stopwatch, it start at time 0 and then 1, 2, 3. So that's why we need those 4 stacked dots. Then we're going to draw those dots coming back, but we're only going to have 4 seconds. We had 5 seconds moving in the positive direction, only 4 seconds in the negative direction. So now we're going to go ahead and add our velocity vectors for the positive part of motion. And you can see that it moves in the positive direction. Now, at this point, we have those stacked dots, and we know that it's not moving, but we said that a velocity of 0 is represented by a dot. Well, we actually already have the dots there. So these dots actually represent 3 things. They represent the time, how many dots, the position, showing that it doesn't change, and the velocity being 0. And then we'll add our vectors in the negative direction, and now we have our completed motion map. Now a motion map is read starting at the axis and away. So when we draw a motion map that has multiple levels like this, you start at the axis and move away. So if you draw it below, it's going to look like this. We'd have a motion map starting at the axis and moving away. Again, it's not read left to right, top to bottom. It starts at the axis at that first dot of time 0 and points away. So you can see each of these motion maps represents the exact same motion. It's just one's drawn above the axis and one's drawn below the axis. So now let's look at another example. Now we're going to draw one where an object is speeding up as it's rolling down an inclined ramp. And I'm going to show the corresponding velocity time, acceleration time, and position time graph. So position time's on top, and velocity, and then acceleration. So I'm going to place the dots as the car rolls and make those graphs. And we're going to look at those graphs. And we can see that the dots are getting further apart as time passes. So what we're going to do is we'll bring those graphs back and compare at the end. But you can see the spacing of the dots gets further and further apart. The time increment is the same. So it's still 1 second each time the dot was placed, but it's getting further and further. So it's traveling a further distance each second. And we'll draw those velocity vectors, and you can see the velocity vectors are getting longer, and a longer vector means that it's moving faster. So it's showing that this object is speeding up, moving to the right or the positive direction. So we have our position and time dots, we have our velocity vectors, and since the speed is changing, we're going to add acceleration vectors as well. So what we're going to do is we're going to look at each of these vectors. We'll take the first one and redraw it, and the second one and overlay it. And the difference of those two, going from the beginning of the end of the first to the end of the second, is a difference of this length, which is the change in velocity, and over a period of time, that's called acceleration. So we can do that for each pair of vectors and see that the change in length of the vectors is the same, meaning the change in velocity over that period of time is the same, meaning the acceleration is the same. So the acceleration vectors are all going to be drawn constant. Now we ran out of vectors to continue to show this change, but we know that since the ramp is the same incline, it's going to have the same acceleration. So the length of each acceleration vector is going to be the same all throughout. And notice we also only have one acceleration vector drawn above each dot. You're not going to fill in space. The vectors will either get closer together or get further apart, just as the dots do. So you should have one acceleration vector, one velocity vector for each position time dot. Now we can compare our motion map to the graphs that we created. So we can see that the acceleration vectors are pointing to the right, meaning we have a positive acceleration. So we know from our previous videos that if we look at the slope of a velocity time graph, that shows us the acceleration. So that slope is positive, so that means that the velocity time graph and acceleration vectors match up. And then we can look at our acceleration time graph, and it's roughly a horizontal line. Acceleration is a little tough because of the little bumping of the car with the marker might have caused the acceleration to change a little bit, but you can see that the acceleration is relatively constant and drawn above the time axis, which means that it's positive as well. So you have a positive acceleration, both the velocity and acceleration graph, and that position time graph has a concave up. Its concavity is opening upward, showing a positive acceleration. So all four things match up. Our acceleration is positive on each of our graphs and on our motion map. So let's look at another example. We're going to have a free rolling car rolling up a ramp and coming to a stop. So it's just going to reach that point. We're not going to draw anything beyond that point. We don't know if it ends up coming back down or rolling up. So we know that as it rolls up, it's going to slow down. So the spacing of the dots are going to get closer together to show that it's slowing down. And then we're going to draw our velocity vectors going all the way to the next dot to show that it is getting shorter and shorter, showing slowing down. And that last one is going to be a spot where we're just going to leave no vector. That's the point where it reaches its highest point, so it's no longer moving. To add our acceleration vectors, we're going to look at the difference of each two succeeding velocity vectors. And we can see that when it gets shorter, our acceleration is actually going to be changed, or velocity changes in the negative direction. So this is what we're going to do for each of those pairs of vectors, is we're going to find the difference of them, but they're pointing to the left this time because the velocity vectors are getting shorter. So each vector that we draw and we find the difference of those shows that the acceleration now is pointing to the left. And for the last one, what we're going to do is we're going to look at that in 0. So the acceleration vector is going to be the same length as that last vector. And our last dot, we're going to put an acceleration vector because we don't know what happens after that, if it stops or if it continues to move back down the ramp. So this is the velocity, position, time, acceleration for our motion map for an object rolling up a ramp and slowing down. So now let's compare our motion maps. So here was the object that was speeding up, moving in the positive direction, and this is the object slowing down in the positive direction. Now notice that what's going on with the velocity vectors and acceleration vectors when it was speeding up. The acceleration vectors and velocity vectors both point the same direction when it was speeding up. And on the motion map on the bottom, when it was slowing down, the acceleration vectors point the opposite direction of velocity. Now, this is always going to be true that velocity and acceleration will point the same way when speeding up and opposite way when slowing down. So that's how you can represent on a motion map that an object is speeding up or slowing down. If you know it's slowing down, acceleration should point the opposite way of velocity. If you know the object is speeding up, that means that acceleration should point the same direction as velocity. Now what happens when it's moving in the negative direction? So if an object speeds up in the negative direction, the dots get further apart. Well, acceleration vectors point the same direction as velocity, so they're going to point to the left like velocity does. So this shows an acceleration that's negative but means speeding up. And then we have an object slowing down in the negative direction. The dots are getting closer together. The velocity vectors are getting shorter. And we know if an object's slowing down, acceleration points the opposite direction of velocity. So here we have a positive acceleration, but yet it's slowing down. So you can't just look at the sign on acceleration and tell what's going on with the motion. The acceleration just tells us that what's going on with velocity compared to the direction. So if they have the same sign, acceleration and velocity have the same sign, that means speeding up. They have opposite signs, that means slowing down. And that's depicted in our motion map by showing opposite direction or same direction for velocity and acceleration. Now let's draw a motion map for an object that changes direction. So it rolls up and then back down. So we know when an object rolls up the ramp, we drew this motion map previously, and it rolls up and it slows down. Now, if we look at it and it rolls up the ramp but then comes back down, what we're going to do is that very end, when we know it changes direction, that means we change levels. We're not going to draw that dot in the very end. We're going to draw it up above. And then that velocity vector and acceleration vector are both going to be pointing to the left as well. And then we can draw the object as it speeds up in the negative direction. And we can see that the acceleration, regardless of the direction that it's moving, is always going to be negative. So that means slowing down when it was moving in the positive direction and speeding up when it moved back down the ramp in the negative direction. So the acceleration direction doesn't change, but the velocity direction changes. It was slowing down and then turned around and sped up. It only stopped for that brief instant in time. So now we're going to draw it for rolling up a ramp and then coming to a stop for a period of time. So it doesn't matter how long, we're just going to represent a period of time. So much like the last one, we're not going to draw that last acceleration vector. We're going to stack those dots at the very end. So it slows down on the way up and then comes to a stop. So now those stacked dots represent four things. They represent time and position. They represent a zero velocity, but they also represent a zero acceleration as well. So when we stack dots, when an object is stopped, it's not moving, it's not accelerating, it's staying in the same position, but time is still passing, which is why we draw more than one dot to show that it stays in that same position. Now our final example is going to be an object that is moving at a constant speed after it has sped up. So an object's going to speed up for 4 seconds. So we know what that looks like when it speeds up for 4 seconds. But when it reaches a constant speed, we're not going to put an acceleration vector above that last dot. So remember, when it speeds up, acceleration and velocity point the same direction. But when it's moving at a constant speed for 2 seconds, remember 3 dots for 2 seconds, the spacing of those dots is the same. The length of those vectors is the same. And if it's moving at a constant speed, that means we have an acceleration of 0. So we still have to draw an acceleration vector, but an acceleration vector has a length of 0 is just a dot. So we represented those acceleration vectors with a dot. So this shows an object that's speeding up into a constant speed. It has an acceleration, but then it doesn't. So let's recap our motion maps. Let's look at the dots. So what do the dots represent? They're position and time dots. So each dot is placed above the number line to show the position of the object. The first dot shows the starting position and a time of 0. Then each succeeding dot represents a defined increment of time. 1 second is assumed unless stated otherwise. If we look at our velocity and acceleration vectors, the length of our velocity vector shows the speed. Shorter means slower, longer means faster. The direction the vector points shows the object's motion. The acceleration vectors show the change in velocity over our increment of time. So that was either positive or negative, depending on the difference of those two velocity vectors. When the acceleration vectors point the same direction as the velocity vector, the object's speeding up, and vice versa. When they point opposite directions, that means the object is slowing down. And when acceleration is 0, the object is moving, that means we draw a dot above each succeeding position time dot. If it's stopped, you just stack the dots. So after you draw your motion map, we want to make sure our graphs and our motion maps all check out. So if an object is speeding up and you want to check, do the acceleration and velocity vectors point the same direction? And if it's slowing down, do our acceleration and velocity vectors point opposite directions? And then we want to check that the direction of the acceleration matches up with each of our graphs, the acceleration time graph, the velocity time graph, and the position time graph. So if the acceleration vectors are positive, does that mean our acceleration time graph is drawn above the time axis? If it's not, then that means it doesn't match up. Does the slope on our velocity time graph, is it positive? It doesn't matter if it's drawn above or below the time axis. It just matters that it has a positive slope. So if we have a positive pointing acceleration on our motion map, we should have these three things. The last one being that the concavity of our position time graph should be curving and opening upward. And then the opposite is going to be true if we have acceleration vectors pointing to the left. Our acceleration time graph should be drawn below the time axis. The slope on our velocity time graph, no matter where it's drawn, should have a negative slope. And the curvature of our position time graph should have a downward opening concavity. So this is the introduction to motion maps. I hope this was helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at